We're going to talk about exponents and exponential functions today. Recalling the definition that a to the r, where r is rational number, if r is m over n, then for appropriate values of m and n, a to the m over n is either the nth root of a, then raised to the m power, or taking the nth root of a to the m. I usually choose whichever one gives me smaller, easier numbers to work with. For example, here we have 16 equals 3/4, or 16 to the 3/4. Well, I would probably do that as the fourth root of 16 cubed. Because if I did 16 cubed, I don't know what that is. But the fourth root of 16 is 2 cubed is 8. That makes it numbers I can easily work with. Let's evaluate these functions. 3 squared is 9. Negative of 5 squared is a negative 25. Only the 5 is squared here, and then I put the negative with it. This one I have parentheses, so it's the negative 5 that is squared, and negative times 5 times negative 5 is 25. 16, the half root of 1/2 to the 1/2 power, is really the square root of 16, or 4. Remember, a negative exponent means, this means 1 over 4 squared, or 1 over 16. 1/2 cubed, 1/2 times 1/2 times 1/2 would be 1, and 2 cubed is 8. 1/2 to the negative 3 means I take the negative, I take the reciprocal of this would be 2 cubed, that's 8. Anything to the 0 power is 1. And this is negative of something to the 0 power, so it would be negative 1. Now here we have some more rational roots. So 27, the negative means we take the reciprocal, 1 over 27, and now I want the third root of 1 over 27, that's 1/3. 8 to the negative 2/3, well, I'll take the reciprocal, 1/8 to the 2/3, or the cube root of 1/8 squared. Well, that's 1/2 squared is 1/4. 64 negative to the negative 1/2 power would be, the negative will make it 1 over 64 to the half power, which is the square root, so 1/8. 9 to the negative 1/2 be 1 over 9 to the 1/2, and the 1/2 power is the square root, so the square root of 9 is 3, and this is 1/3. In this section, we're going to extend the definition for a to the r to include all real values, not just rational values of the exponent r. So now we can have some square roots. For example, 2 to the square root of 3 might be evaluated by approximating the square root of 3, exponent with the rational numbers, 1 and 7/10, 1 and 73 hundredths, 1 and 732 thousandths, and so on. Since these decimals approach the value more and more closely, it seems reasonable that the square root of 3 should be approximated more and more closely by the numbers 2 to the 1 and 7/10, 2 to the 1 and 73 hundredths, 2 to the 1 and 732 thousandths, and so on. Recall, for example, that 2 to the 17 divided by 10 would be this 10th root of 2 raised to the 17th power. And that's really how 2 to the square root of 3 is defined in a more advanced course. To show this assumption is reasonable, we're looking at the graphs for the function f of x equals 2 to the x with different domains. Here the domain is the integers, and so we just have these points. Here, selected numbers from the domain, rational numbers. You notice we're getting the same, looks like the same curve, but it's filled in more. And if we do all real numbers as the domain, we can get the solid curve, and here would be 2 to the 1/3, or the 2 to the square root of 3 power. Using this interpretation of real numbers, all the rules and theorems of exponents are valid for all the real number exponents, not just rational ones. And in addition to that, the rules for exponents we already have, we use several new properties in this chapter. For example, if y equals 2 to the x, then every real value of x leads to exactly one value of y, and thus this is a function. So the exponential function. If a is greater than 0 and not equal to 1, then f of x equals a to the x defines the exponential function for base a. The independent value x can be any real value. This is base a. Notice a cannot equal 1. Well, do you know why? The reason is if we had a was 1, 1 to any power would still be 1, and so it would not be a one-to-one function. Now, the exponential functions. Earlier slide, we had a graph of 2 to the x with different domains, and here we're going to use the domain of all real numbers. Repeating that one. The y-intercept, where y equals 2 to the 0, equals 1. Right here. That's the point 0, 1. Since 2 to the x is greater than 0 for all the x's, you can tell it's for all the x's, and as x goes to negative infinity this way, it actually gets closer and closer to 0. That's what this limit means. This stands for limit. The x-axis is a horizontal asymptote. It's a line that the graph never crosses. So as the graph suggests, the domain of the function is from negative infinity to infinity. The range is open parentheses 0 to infinity. The function is increasing its entire domain, and actually is. It would pass both a vertical and horizontal line test, so it's a one-to-one function.